So let's set up the integral. What is it that we do? Well, we think of time. The time runs from values a to b. We subdivide that time interval into short subintervals of length delta t. Those times are denoted ti, so that's just standard notation. And then you look at one of the intervals. So during that interval, the interval from ti to ti plus 1. What is it that we observe? So we have position f of ti there. We have position f of ti plus 1 next to it. And we are interested in the area. So, what is it that you have? Area of this ith triangle. The contribution of ith part of the motion is approximately a half of the determinant made by two vectors. One is from origin to the f of ti, from origin to f of ti. The other is the displacement vector from f of ti to f of ti plus 1. But we want that to be in a linear way, to be expressed in terms of delta t in a way that we have something times delta t. So we keep working on that. And so what do we do? Well, delta t should come from there. So how is it coming from there? Well, we say that the displacement is approximately, so we do approximation again. Approximately the velocity at the time ti. So velocity is f prime of ti, and that is a vector multiplied by the time spent, which is delta t. And then algebraically we can pull this constant, this coefficient, out of the product, because we treat this area as a product of two things, so that delta t comes out. So the result is a half of the area on this vector, position vector, and velocity vector, multiplied by delta t. And then once we have ith area in this special form, we are ready to say that the total area is sum of those ai's, and that is approximately the sum of all i's of those things, a half of area on position vector and velocity vector times delta t, and then area is equal to the limit as delta t goes to 0 of those sums. And at this point we recognize an integral. A equals an integral as the variable, the time, changes from a to b of that function 1/2 area, algebraically determinant, right, on the two vectors. One is from origin to the position point, and the second is the velocity vector. So that's what we have to integrate here. So that's it. We found the formula for the area swiped by radius vector